All right, so we're going to do double angle identities, section 7.4. And I'm going to start off with an example. Now, this example isn't actually a double angle identity example. Here, we're actually going to start with cosine of 3x equals root 2 over 2 over the domain x between 0 and 2 pi. Okay. Now, here, what we're going to do is we're going to let 3x be u so that this looks more like something that we know how to solve. Okay, maybe I'll just put in here let u equal 3x. And so now we have, let's space this out a little bit. Now we have that cosine of u is root 2 over 2. Now root 2 over 2 should hopefully jump out as being special because 2 is the same thing as square root of 2 times square root of 2. And root 2 is the same as root 2 times 1. We can divide the numerator and denominator both by the square root of 2 and get 1 over root 2. So in fact, root 2 over 2 is the same thing as 1 over root 2. We've mentioned this before in class. And so there you have it. So this is in fact a special angle. This should be ringing bells that we've got this triangle here, 1, 1, root 2, where we have 45 or pi over 4 and 45 pi over 4 in both of our acute angles there. So we can solve this. We can say cosine of u, we can say that u equals, 45 certainly, or pi over 4. We can see that our domain is up to pi over 2, so we're looking for radian solutions. And we can go around the unit circle to get our other solution or solutions. So we have here pi over 4. And we have, of course, all students take calculus. So that tells us that cosine is positive here and here, and we have a positive root 2 over 2. So we can ignore those two quadrants, but we're also going to get a solution in quadrant 4, where we get 2 pi minus pi over 4, which is 8 pi over 4 minus 1 pi over 4, 7 pi over 4. Okay. Now, this is what u equals. But don't forget, we let u be a dummy variable for x. Okay. So I need to replace this u with 3x. I have 3x equals pi over 4 and 7 pi over 4. How do you solve for x? Well, you divide both sides by 3. It's okay that we have two solutions listed here. We just divide each of them by 3. So I get x equals pi over 12 and 7 pi over 12. Okay, now you might think that that's the end of the story, that this is the final answer, but it is not. I made a mistake on purpose, and I want to talk about that now. So none of the algebra is wrong. None of the trigonometry is wrong. What's wrong is that I didn't actually get all the solutions. So have a look here. Pi over 12 and 7 pi over 12. Pi over 12, well, that's pi over 4 divided by 3. That's a very small angle like this. 7 pi over 12. Well, that's 7 pi over 4 divided by 3. 7 pi over 4 is this right, is this right here. But then divided in 3, well, roughly sort of 1, 2, it's something like that. Okay? So the problem is we haven't actually gotten all the solutions in a full circle. Our domain is that x goes from 0 to 2 pi. The problem is this part, we got all the solutions from 0 to 2 pi. But when we divide by 3, we're not going all the way around the circle anymore because our solutions, this purple one, was here. It shrunk all the way down to here. So to solve this issue, it's not actually that complicated. What we need to do is recognize that when we let u equal 3x, that will also change our domain here. So what I'm going to do is I'm going to take x equals 0 as my lower bound, and x equals 2 pi as my upper bound. And I'm going to substitute each of those into my let statement. That will give me a lower bound for u of 3 times 0, which is 0. And it will give me an upper bound for u of 3 times 2 pi, which is 6 pi. So in fact, the domain on u is 0 to 6 pi. Sorry, that should have said pi there. 0 to 6 pi. So I'm going to write that right in here. 0 is less than or equal to u is less than 6 pi. In other words, 0 has been multiplied by 3 to get 0. 2 pi has been multiplied by 3 to get 6 pi. And so now on this step right here, I don't stop at 2 pi. I have to stop at 6 pi. So I have to go around the circle a few more times. I got the first solution, pi over 4. I got the second solution, which was 2 pi minus pi over 4. I'm going to get a third solution, 2 pi plus pi over 4. That will land me on here again. So I get 2 pi plus pi over 4. That's 8 pi over 4 plus 1 pi over 4, 9 pi over 4. I'm going to have another solution when I go 2 pi, 4 pi minus pi over 4. Right? That's less than 4 pi, which is certainly less than the 6 pi that is our limit. So this is 8 pi over, this is 16 pi over 4 minus 1 pi over 4. That's 15 pi over 4. And what else? So let's see here. We got pi over 4, 7 pi over 4, full circle plus pi over 4. So this is one circle. Full circle, well, 2 full circles minus pi over 4. So this is 1 circle plus something. And now we want to go up to 3 full circles. So we'll have next 2 circles, 2 pi, 4 pi, plus pi over 4. That comes in here. And the very last one will be 2 pi, 4 pi, 6 pi minus pi over 4. And there's no more after that because our limit really is 6 pi. This little number here is to show how many full circles I have. I have a full circle plus a pi over 4 a full circle plus a bunch. It's actually 2 full circles minus pi over 4. 2 full circles plus a pi over 4. That's this one here. This is 16 pi over 4 plus 1. That's 17 pi over 4. And lastly, 3 circles minus a pi over 4. That's 6 pi is 24 pi over 4. 24 minus 1, 23 pi over 4. Now I've properly accounted for the full domain on U. And now I can substitute U is 3x. And I need to list out now all of these solutions. I'm going to get rid of this diagram here. So I have pi over 4, 7 pi over 4, 9 pi over 4, 15 pi over 4, 17 pi over 4, and 23 pi over 4. And I'm going to divide each one of these solutions by 3. That gives me pi over 12, 7 pi over 12. Well, let's just go unsimplified to start with. 9 pi over 12, 15 pi over 12, 17 pi over 12, 23 pi over 12. Now notice 23 pi over 12 is just a smidgen less than 2 pi, right? It would take 24 pi over 12 to equal 2 pi. That's one full revolution of a circle. And we're just a smidgen under that. So in fact, these values really are in the domain that we wanted. Okay? So that's good. I guess as a final step, we should simplify any of those that can be simplified. The third one here can be simplified. So we have pi over 12, 7 pi over 12. Here, divide by 3, 3 pi over 4. Here we can divide by 3 also, 5 pi over 4. That is, divide the numerator and denominator by 3. 17 pi over 12 cannot be reduced. 23 pi over 12 cannot be reduced. That is our answer. Those are the 6 values of x that when you substitute them in right here will make cosine of 3x equal to 1 over root 2, or root 2 over 2. Okay. With that, you can go ahead and do exercise 12E. Okay? Now, let's get into double angle identities proper. So in your textbook, you can have a look at the proofs if you want, but I'm going to just go through and state that sine of 2, should I use theta or x? It doesn't really matter, of course. I'll use theta. Sine of 2 theta equals 2 times the sine of theta times the cosine of theta. Okay? Now this may be a little counterintuitive, but this is true. And you can try it out with pick a value for theta and try it out on your calculator. If you pick, for example, 30, and you plug it in there, this is saying that sine of 2 times 30 is equal to 2 times sine of 30 times cosine of 30. Well, 2 times 30 is 60, so saying sine of 60 is the same as 2 times sine 30 times cosine of 30. What's sine of 60? Well, this is a special angle. It's root 3 over 2. What's sine of 30? Well, it's a half. And what's cosine of 30? It's root 3 over 2. That's also a special angle. And so then these cancel, and you can see, in fact, that we do have a true statement. Root 3 over 2 does equal root 3 over 2. So when we substitute for 30, it certainly works, and it will work no matter what angle you put in. Okay, I happen to pick 30. I chose 30 actually because I know that 30 is a special angle here and here, and that 2 times 30 is a special angle. So that was a nice choice. But you can choose any angle you like, and this identity will hold. This is one that you need to memorize. I'm going to put in another identity here. So another identity, and again, the proof is in the textbook. Cosine of 2 times theta equals cosine of theta squared minus sine of theta squared. Okay, and remember, cosine of theta squared is cosine of theta squared. It is not cosine of theta squared. Okay, so when you see this 2 here, you're basically thinking, that it's going to travel over here and that you're introducing brackets. That's what that means. When you see this 2 here, you're imagining that it travels over here and that you're adding in brackets like that. Okay? So I'm going to come back to this form of this identity. Let's put that on the side as scrap paper. And this identity, which also you should memorize, comes in 3 flavors. So this is my, well, it's not my favorite version, but it's the one that I like to start with. Part of the reason for that actually is just the way I've memorized them. So the sine 2 theta has a sine function followed by a cosine function. Cosine of 2 theta has a cosine followed by a sine. And it's just part of the way I memorize them. Now they're completely different identities. Here it's all multiplication. Here you have squareds and a subtraction. So they're obviously not they have different foundations. But I like to write them this way because it's easier for me to remember them. Now, keep in mind this identity here. We know that sine theta squared plus cosine theta squared equals 1. That's the Pythagorean identity. We actually proved that one just by looking at the new definition of trig ratios. It's not that difficult to prove. So what I can do is I can rearrange this. I could subtract sine theta squared from both sides and get this. And then substitute this here with this here. Okay, so I could get 1 minus sine theta squared, that's cos theta squared, minus sine theta squared from this one right here. And that equals 1 minus 2 groups of sine theta squared. Okay, so what we've just done is showed that this identity here can also be written as this here. I could say that cosine of 2 theta equals 1 minus 2 sine theta squared. Okay, so that's a second identity. Also, and I'll do this in pink, we can come back to the Pythagorean identity and get, again, sine squared plus cos squared is 1. And this time I'm going to isolate sine theta squared. That's 1 minus cosine theta squared. And then I'm going to substitute sine theta squared is 1 minus cos theta squared. I'm going to substitute that right here. Okay, so now I'm going to have cosine of 2 theta. Oh, that's a funny theta. Equals cosine theta squared minus sine theta squared. But I'm going to replace this sine theta squared with this 1 minus cos theta squared. Now I've got to be careful because I have a subtraction, so I'm going to put brackets like this. Okay, let's fix up that C. There we are. Now, if I simplify this, I get cosine theta squared minus 1 plus cosine theta squared, right? Subtracting a negative. And so I get 2 groups of cosine theta squared minus 1. So this gives us the third version of this identity. Whoops. Right here. Okay. So let's put this all together then. You want to memorize the first one. You want to memorize the second one. You want to memorize this one here. And you want to memorize this one here. Now these second two, personally, I will often quickly derive them from the second one and the Pythagorean identity if I forget or double check. Okay? But those you want to memorize. And again, you'll have them. We should double check the formula sheets, but I'm pretty sure that you have them on the formula sheets. But just because they're there doesn't mean that you don't want to memorize them, because you want to notice questions. You want to notice this structure here or notice this structure here and think, I can use an identity. If you don't have it in your head, it doesn't really help, because you're not going to have time to run through the formula sheets and look at all the identities and hope that you find one that matches what you're looking at. You need to be familiar with them anyways. So let's just clean this up here. We have cosine of 2 theta is cosine theta squared minus sine theta squared. That's version 1. Or it can also be seen as 1 minus 2 sine theta squared, or it can also be seen as 2 cosine theta squared minus 1. Okay, those are the 3 versions of this double angle identity. Okay, so those are the new identities. Now let's use them. Okay, I'm just going to scroll up here, scroll back down. Let's get an example here. I'm going to do an example. Suppose sine theta equals 2/5 for theta in the first quadrant. Okay, sine theta is 2/5. Theta is between 0 and pi over 2. And notice that we have pi over 2 here, so we're thinking radians. And I want to find A, cosine of theta, B, sine of 2 theta, C, cos of 2 theta, and D, tangent 2 theta. Okay? Just a quick comment, actually. Whenever you see cosine of theta, for example, this is very, very common notation, but what it really is it's cosine is a function and theta is the argument. You know, we drop these brackets a lot of the time, but they are technically there. This one here is sine of the argument 2 theta. Cosine of the argument 2 theta. Tangent of the argument 2 theta. Okay, just pointing that out. So I'm going to find cosine theta in 2 ways. So method 1 is good to know both. It's not necessarily vital to know both, but it's good to know both. Then I'm going to find B, C, and D using identities. So method 1 for cosine theta, I'm going to come back to some of this trig stuff we've been doing. I've got sine theta is 2 over 5, and we're in the first quadrant. I don't even need to draw all the other quadrants. I've got sine theta, so that's y over r. So my y is only 2, whereas my r is 5. Okay, and there's my theta. And I'm asked for cosine. Well, cosine is x over r. So I'll use Pythagoras to find x. X squared plus 2 squared equals 5 squared. X squared plus 4 equals 25. So x squared is 25 minus 4. X squared is 21. X is plus or minus root 21. But because I'm in the first quadrant, it's going to be a plus or a positive root 21. And now cosine is adjacent over hypotenuse, or x over r. So cosine then is going to be root 21 over 5. Cosine of theta equals root 21 over 5. Done. Okay. Now I'm going to do it another way, just so we can see it. We've got the Pythagorean identity, and so I'm going to just use it directly. I'm going to say sine theta squared plus cos theta squared equals 1. And sine theta squared in this case is 2/5. So I have 2/5 squared plus cos theta squared equals 1. Well, let's multiply out here. We get 4 over 25 plus cos theta squared equals 1. Subtract 4 25ths on both sides. We get cos theta squared equals 1 minus 4 25ths. 1 is 25 25ths, so that's 25 25ths minus 4 25ths, that's 21 25ths. That's cosine theta squared. Now if I square root both sides, I'll get cosine theta. That's what I was asked for. So I'll square root the left-hand side, I get cosine theta. I square root the right-hand side, I get a plus or minus, but we know our answer is going to be the positive one because all trig functions are positive in the first quadrant, and we were told that we're in the first quadrant. So I'll just calculate this here. Cosine theta is positive square root of the 21 over square root of the 25. It's root 21 over root 25, which is root 21 over 5. Okay, same answer as we would expect. So there's two different ways to get cosine of theta. Okay, B, sine theta. Sine 2 theta. So to get sine 2 theta, I'm going to use my identity. So sine 2 theta is the same as 2 times sine theta times cos theta, which is 2 times, well, sine theta was given to us, 2/5. Cos theta we just found, root 21 over 5. So we just multiply these all together. I get 4 root 21 over 25. Done. C. What did C ask for? I think it was cosine 2 theta. It was. Okay, cosine 2 theta. I'm going to use an identity again. Now with the double angle, it's called a double angle, of course, because we have 2 times theta, doubling the angle. The double angle of cosine, we have 3 options to choose from. Cos theta squared minus sine theta squared is one of them, and so that's the one I'll use. When it doesn't really matter which one we use, this is often the one I'll pick. The other two are really good if you only have sine or if you only have cosine, then you would pick one of the other two. In this case, we have them both, so it's no big deal. So now cosine is root 21 over 5. So I'm going to have root 21 over 5 squared minus sine is what, 3/5 was it? 2/5. 2 over 5 squared. So that's going to be 21 over 25 minus 4 over 25. which equals, what is that, 17 over 25. There we are. So cosine of 2 theta is 17 over 25. Next, D. That one was tangent of 2 theta. Now I'm going to use another trig identity. We know that tangent is sine over cosine. So tangent of 2 theta is sine of 2 theta over cosine of 2 theta, which, well, we just found them. Sine 2 theta, there it is, 4 root 21 over 25. Over cosine 2 theta, 17 over 25. And we just do the fraction division. That's 4 root 21 over 25 divided by 17 over 25. Keep change flip. 4 root 21 over 25 times 25 over 17. Those cancel. We're left with 4 root 21 over 17. That's tangent of 2 theta. Okay? So that's how to do a question like that. We're using the identities to, well, in order to solve for things that otherwise directly would be quite complicated. Right? Okay. Next, let's take another example here. Let's suppose we have cosine of theta equals negative a half. And theta is obtuse. The question is, find sine of theta, cosine of 2 theta, sorry, sine of theta, sine of 2 theta, then comes cosine of 2 theta. The order might not really matter, but that's the order I have them here. Sine 2 theta, cosine 2 theta, and tangent 2 theta. See, now when I look at this, I'm already thinking, okay, well, the tangent is pretty straightforward because it's just going to be the ratio of the previous two, right? Because tangent of 2 theta is sine of 2 theta divided by cosine of 2 theta. Okay, A, sine of theta. I'm going to do this in two ways. Maybe this time I'll do it the algebraic way first. Well, no, I'll stick with the same order. Okay, so the first way is going to be looking at it through trigonometry. Now, when we say that theta is obtuse, that means that it's greater than 90 degrees, but it also means that it's less than 180. Okay, an obtuse angle is one that is greater than 90 but less than 180. If it was greater than 180, it would be called a reflex angle. And if it equaled 180, it would be called a straight angle. And if it equals 90, it's called a right angle. Okay, but an obtuse angle is between 90 and 180. So we know that it's in quadrant 2. We also know that cosine is negative 1 over 2. And so the x direction here has to be half as big as the radius. So there's my picture of this obtuse angle. And that's all I need to really find anything I want. I can use Pythagoras to get this y value, which I'll do right now. So I have negative 1 squared plus y squared equals 2 squared. 1 plus y squared equals 4. Y squared equals 3. Y equals plus or minus the square root of 3. And in this case, we can see it's plus the square root of 3 because we are above the x-axis. Y is positive. We went up. And so I can answer anything. So if I'm going to answer what sine of theta is, I say, oh, okay, well, it is y over r. It is root 3 over 2. And I could check with all students take calculus. All students, S, sine is positive in this quadrant, and sure enough, there it is positive. Okay. So that's fine. Now let me do it the other way. Let me do it with the identity, the Pythagorean identity. We have sine theta squared plus cosine theta squared equals 1. So we have root 3 over 2 squared plus cosine theta squared equals 1. Oh, sorry, what am I talking about? I'm starting with the answer. No, we don't know what sine theta is. Let's come on back up to the question here. We know that cosine theta is negative a half. Okay, so I have negative a half squared right here, and I have my sine theta squared here. That's what we're trying to solve for. I have sine theta squared plus negative times a negative is a positive, so we have 1/4. Okay. Subtract a quarter from each side, I get sine theta squared equals 1 minus a quarter. That's 3/4. And to solve for theta, I'll square root both sides. Square root the left, I get sine theta. Square root the right, I get plus or minus root 3 over 4. Now I'm going to break that up. I know that sine theta has to be positive because I'm in this quadrant here. So I can ignore the minus. I'll just get rid of that right now. And I'll square root the 3 and square root the 4. So I have the square root of 3 over the square root of 4, which is 2. Okay? So that gives me sine theta is root 3 over 2, which is exactly what we have right here. Two different ways to do it. Okay, B, sine of 2 theta. So here I'm going to use an identity. That's 2 times sine of theta cosine of theta. Sine of theta is root 3 over 2. And cosine of theta was given to us as negative a half. Okay, and I just multiply them. Okay, 2 is 2 over 1, so those go. I'm left with negative root 3 over 2. Simple. Sine 2 theta is negative root 3 over 2. C. Okay, so C is cosine of 2 theta. Cosine of 2 theta. Now I'm going to use my my identities for cosine. That's cosine theta squared minus sine theta squared. Cosine theta squared. Well, cosine theta, where did it go? Cosine theta was negative a half. So we have negative 1/2 squared minus sine theta. What sine theta again? It was root 3 over 2. Root 3 over 2 squared. And we just calculate. So this is positive 1/4 minus 3/4. Okay, because negative 1/2 squared is negative 1/2 times negative 1/2, which is positive. 1 times 1 is 1, 2 times 2 is 4, positive 1/4. And root 3 over 2 squared is root 3 over 2 times root 3 over 2. Root 3 times root 3 is 3. 2 times 2 is 4. Okay. And 1/4 minus 3/4 is negative 2/4, which is negative 1/2. There we are. D, tangent of 2 theta. Well, that's just going to be sine of 2 theta divided by cosine of 2 theta. Sine we already got is negative root 3 over 2 over cosine we just got, that's negative 1/2. Keep change flip, so we have, well, let's just even ignore the negatives already. A negative divided by a negative is a positive, so I'm just going to get rid of my negatives on the next step. I have root 3 over 2 divided by 1 over 2. Keep change flip, root 3 over 2 times 2 over 1. We're left with root 3. So the tangent of 2 theta is root 3 in this case. Okay, I'm going to do one more example here, and then that'll be it for this section. Let's suppose we're asked to solve sine of 2 theta equals sine of theta for 0 less than or equal to theta less than 360 degrees. Okay. There are a few questions like this in the textbook, number 5 on page 522. They're very good questions. 6 and 7 are also good questions. So before I even do anything, I just want to remind you of this. If we have x squared equals x, for example, you cannot, let's actually change this up a little bit. Let's say x onto x minus 1 equals x. If you're trying to solve for x there, you cannot divide both sides by x and say that therefore x minus 1 equals 1. You cannot do that. Okay? Or to make it even a little bit more clear, let's suppose we had, instead of x all by itself, it was a 2x. Okay? You cannot divide both sides by x and say, oh, well then x minus 1 equals 2, x equals 3. The reason you cannot is because you lose a solution. When I substitute 3 back in here, and here, and here, I get 3 onto 3 minus 1 equals 2 times 3. 3 times 2 equals 2 times 3. Yes, it does. So I get a solution, but I've also lost a solution. The correct way to proceed, if you have a question like x onto x minus 1 equals 2x, is to bring everything to one side and factor. Okay, so here I have x squared minus x equals 2x. I subtract 2x on both sides, like so. I get x squared minus 3x equals 0, and I factor. I get x onto x minus 3 equals 0. The only way for this times this to equal 0 is if the first one equals 0 or the second one equals 0. So I have to solve those two equations separately. This gives me x equals 0 or x equals 3. Those are my two solutions. The first time, when we just canceled out these x's, we lost the solution of 0 and only had the solution of 3 left. Here I get both. Notice 0 really is a solution. If I put 0 here, here, and here, I get 0 times 0 minus 1 equals 2 times 0. Well, 0 times negative 1 equals 0. Yeah, of course it does. Okay. So I want to point this out because I see some of you doing this. I've pointed it out before, and some of you are still doing it. Really, really, really important. And this is going to come up in a question like this. Okay, so I'm just going to take this entire question and bring it down. I'll copy it here. And we'll do this one. And there are several similar questions in the textbook. So I'm looking at this question and I'm seeing that this argument 2 theta and this argument theta are not the same. I need them to be the same. Okay, I can't solve for theta when I have arguments embedded in trig functions that are different. So I use a trig identity. I rewrite sine 2 theta as 2 times sine theta times cosine theta equals sine theta. Okay? Now here, you do not divide both sides by sine theta to get 2 cos theta equals 1. You do not do that. Why? Because you lose solutions. You must solve equal to 0 and factor, just like in this previous example up here. So I have 2 sine theta cosine theta minus sine theta equals 0. I'm subtracting sine theta on both sides, setting it equal to 0, just like we do with polynomials, setting it equal to 0, right? And now I can factor out a common factor of sine theta. If I factor out sine theta, well, I can leave the 2 there. Sine theta, actually, let's just do this just to make it, okay, let's just keep going. So I'm going to factor out sine theta, sorry. I'm going to factor out sine theta, and I'm left with sine theta times what equals this? Well, the parts that are not underlined in red, 2 cos theta. Sine theta times what equals this? Well, 1. Okay. Now that I've factored it, how do I solve this? Well, I set this equal to 0 and this equal to 0. Because any values of theta that make this equal to 0 or make this equal to 0 or make them both 0 at the same time will make the entire equation 0. Just like before. So I split this up into 2 separate questions. Sine theta equals 0 and 2 cos theta minus 1 equals 0. Okay? Sine theta equals 0. This is on our special angles chart. We're given that we're going to do one circle. And do we include? No, we don't include 360. That's actually important here. So sine theta equals 0 when theta equals 0 degrees or 180 degrees. And we can see that by remembering the new definition. The new definition of sine is y over r. How could y over r equal 0? Well, when y equals 0. That's the only way. When does y equal 0? Well, right at the very beginning, when this is at 0 degrees, y is 0. That's this answer. And as we go along, okay, y is not 0, y is not 0, y is not 0, y is not 0, but here it is again. Y is 0. Y is 0 at 180 degrees. And then if we go around further, y is not 0, it's negative, y is not 0, it's not 0, it's not 0, it's not 0, it's not 0. Right here, y is 0 again at 360. That's why I went to check that it wasn't less than or equal to, because if it said or equal to, we would have to put 360 as an answer here as well. But it didn't. It just said strictly less than 360. So we just have these two values here. Now, that's for the sine theta equals 0. Now we have to do 2 cos theta minus 1 equals 0. Well, this is a little bit of algebra. I'll add 1 to both sides, divide both sides by 2, so I get cos theta equals a half. Special angle. And I'll go through. Okay, we've done a number of these, so it should start to come a bit faster. Cos of what is a half? 60. Okay, that's right here. So we have cosine of 60. We also have all students take calculus. This is positive. So here is the other quadrant, quadrant 4, where we get a solution. That will be 360 minus 60. Okay, so we're going to get 60 and we're going to get 300 as our two values for this equation. So altogether then, we have 0 and 180, and we also have 60 and 300. So altogether, we have theta equals 0, 60, 180, I'm doing them in order, and 300. Okay, and all four of these, if you took any one of these and you plugged it back in, here and here, you would get a true equation, right? That's what we've done. Okay, that pretty much covers it. So here now we're up to exercise 12F. Okay, so from this section we got one example up here right off the top that's not a true double angle question where we let u equal the argument. And questions like that come in exercise 12E. And then we also have exercise 12F.